In this application problem, applications of rational functions, we're told that you and your family are driving to San Diego on a road trip. From Phoenix, the trip is 354.5 miles according to Google. Answer the following questions based upon this situation. So use the relationship distance equals rate times time to write a rational function t of r that has the average rate of travel r as its input and the time of travel in hours as its output. The distance will be constant at 354.5 miles. So what I'm going to do first is I'm going to take this equation, d equals rt, and I'm going to solve for t. So I'm going to divide both sides by r. So d over r equals t. Then I'm going to substitute 354.5 miles for d. So 354.5 over r equals t. I now have it written as a function of r. So I can write this from left to right as I'm used to seeing my functions. T of r equals 354.5 divided by r. So there is my function for time output with rate of travel input. Part B, provide a rough but accurate sketch of the graph. Label your horizontal and vertical axes. You only need to graph the first quadrant information. So let's go over to our calculator. And for y1, we're going to enter 354.5 divided by, in this case, x. And let's go to window. So since the input is rate, I'm going to start with 0, and I'm going to go up to like, 90 miles an hour. And then for my y min, which is my time, my y value is my time, so I'm going to start at 0, and I'm going to go up to, it's probably not going to take us that long, so let's say 20 hours. So x's are rate of travel, y's are time. So these are just a guess to give me a pretty decent shape, but I do know I want all the values in the first quadrant, so everything's going to be positive. So let's press graph and see what we get. Oh, there we go. So that's not too bad. I'm going to go ahead and go with that. So I have time is my vertical axis, rate is my horizontal axis, and I'm going to draw this graph, look something like this. And let's go back to window. I had 0 to 90 and 0 to 20. So this is really r, and this is really t. All right, let's go back to graph. So if you average 60 miles an hour, how long will the trip take? So t of 60, input is 60. That's going to be 354.5 divided by 60, and that's approximately 5.9 hours. So as a complete sentence then, we have at an average of 60 miles per hour, the trip from Phoenix to San Diego will take about 5.9 hours. Part D, if the trip took 10 hours, so that's a time value, what was your average rate of travel? So time, that's an output, equals 354.5 over r. I can multiply both sides by r, which is going to clear the r here and put r on the left. Now I divide both sides by 10. So r equals 35.45 miles per hour. So as a complete sentence, if the trip took 10 hours, your average speed was 35.45 miles per hour. Now for part E, determine the horizontal asymptote for t of r and explain its meaning in this situation. So what I'm looking for then is as r gets really big, so as r approaches infinity, t P of R is going to approach, and what I have is 354.5 over R. So as this number, this R, gets really, 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 really big, the outputs for this fraction are going to approach 0. And you can kind of see that on the graph, that the faster I go here in this direction, the less time it would take me to get to San Diego. I mean, there is a point of diminishing returns. You can only go as fast as your car will go and as fast as traffic and speed laws will allow, of course. But so in general, then, as our rate gets faster and faster, so we can explain that here, as rate increases, time decreases. For our vertical asymptote, we want to find the value of R that makes the denominator 0. Well, the denominator is R, so R equals 0 makes the denominator 0. So that's the vertical line that goes through the vertical axis right here. That's the vertical asymptote. It's the guiding line for the function. But what it really means here in the context of this problem is that our rate for this model cannot equal or will never reach 0. So we'll never be standing still in this model for the trip to San Diego.